Okay, good afternoon. So today we're going to this afternoon we're going to discuss the mechanical principles of uh, kinetics. So going back, so mechanical principles of kinetics. So when we talk of kinetics, it refers to the motions. So how do we determine the motions? That's the basic question. Or what determines the motion? So there are five determinants of motions. First, we have the type of motion, location of the motions, magnitude of the motions, direction, rate of motions, or rate of change at which the motion occurs, which refers to the velocity. No? So these are the determinants. So type of motions, whether it is smooth or rough or rugged. No? Location where we can find it. Is it along the sagittal, along the uh, coronal, no? Magnitude, how strong it is, or how much force is used to produce this motion. Direction, where it is going. Is it going to downward, upward, or medial to lateral side? So that refers to the direction. Rate of motion, how fast and how slow is the motion. So forces. So basically, in order for us to move, we need to have forces. Okay, so kinetics is the study of forces acting on the body. Motion occurs because of this force. Without force, we cannot produce motion. Displacement is the motion of a body or segment that occurs where when force is applied. So displacement is the measure, no, from point A to B. Now from point A to B, there's a motion that happens. No? So a force is a push or pull that produces displacement. So and displacement is a vector quantity, diba? Because it has a direction, whether point A to point B is going to the north or going to the south. Okay. So forces have two dimensions. You have the magnitude, which refers to the amount that it is applied, and second, direction, whether it's going to the north or to the south or west, up or down. So therefore, the direction of this displacement is dependent on the direction of the force. Now these two always goes together. Okay. So whenever the force go, it is where your direction of displacement also. Type of forces acting on the muscles. Okay. So there are several types of forces that is acting on the muscles. Number one, you have the gravity. The gravity is the most prevalent force that all structures encounter. Gravitational force is commonly referred to as the weight of an object or body. Muscles muscles produce forces on their bone segments by either active contraction or passive stretching. So the muscles produces uh, forces when it contracts, or when you say contract, when it exerts effort. So the contraction of the muscles could be in concentric or shortening, or it could be in eccentric or lengthening, whether the other side is being passively stretched and the other side is actively contracting. So let's take for example, when your biceps muscles contract, okay, it shortens, while the other side, the triceps, is being passively stretched. Okay. Now, externally applied resistances. These devices are numerous and are whatever the muscle must work against to produce motion. So these are external applied resistances. So basically, friction is one of that resistance. So when we move our body segments in air, we encounter resistance. This resistance is in the form of air friction, diba? Hangin. So you can easily encounter air friction when you are riding in a vehicle, especially in motorcycle. Okay, so when the air hits your body, it encounters resistance. Or we call that as drag, no, in car racing. Okay, so fraction is the resistance to movement between two objects that are in contact with each other. So inana siya. So resistance na siya nga ma-encounter sa itong body. So we could have also load. When you say load, nang i-apply na to nga, let's take for example, if you're carrying an object, that object is considered as load. Load can offer resistance against the uh, movement of the body or against the motion. Diba? Kay always, ang direction sa load is always towards the gravity, no? Goes with the gravity. While ang muscle contraction always goes against gravity. Let's take for example when you stand. So when you stand in upright position, or when you put your body in upright position rather, it encounters resistance against gravity. Ana siya. No? The mass is the amount of matter contained within an object, whereas weight is the force of gravity acting on the object. So that is different from mass, no? Weight. So weight is only actually it refers to the amount of force applied by the gravity or exert by the gravity in our body. When I say weight, which is depending also on the amount of mass within the body. So the unit of mass is in kilogram or in pounds, while the unit of weight is in Newton because it is a force. So therefore, if you are going to measure your weight in the weighing scale, you measure there the amount of force, not the mass. Okay? Kay weight man kaha na weighing scale. Nya nganong kilogram, why ang the unit is in kilogram, which is supposedly it is in Newton. So therefore, you are measuring there not the weight but rather the force should be in Newton. So you should multiply it by 9.8 meters per second squared if it is in kilogram. If it is in pound, then you have to multiply it by 32 feet per second squared, which is the acceleration due to gravity. So a moment is the result of force acting at a distance from point of motion or the axis. In mathematical terms, a moment or m is the product of distance and the force. So this is the formula of your moment. Moment is equals to d times f. D refers to the distance, actually uh, towards the axis of rotation. Okay, and F is refers to the force. This force is the amount of force applied in order to move the object. So in translational forces, D is the length of the lever arm or the perpendicular distance from the force vector to the center of motion. But in rotatory force, the lever arm is the moment arm or the perpendicular distance from the force vector to the axis of motion. Okay? So inani siya. Ang imuhang Kung translational force, when you say translational, if the motion produced is in straight line, it is not in rotatory. No? So your D is equivalent to the lever arm. Lever arm is the perpendicular distance from the force vector to the center of motion. When you say center, where does the motion occur? No? Dito na siya taman. Kung na siya imuhang lever arm. So we can relate it to now to the fulcrum. No? But in rotatory force, lever arm is the moment arm. When you say moment arm, mo to siya nag-move ba? No? Kung asa dapit to ang force active dapit, then asa dapit ang where is the axis of rotation? When you say axis, the fixed point where that object moves around, no? Okay, rotational, it is rotational forces man. So perpendicular, take note of the word perpendicular means 90 degrees. Okay. So let's take for example now here, we have a picture. So we have here the muscles, the iliopsoas or the hip flexor muscles. So we have here the load. Okay. So if I'm going to move, no, the leg in straight flexion, so we have here, this is now your perpendicular distance. From here up to this point, this is now perpendicular distance. Okay, so we can say that this is a what? Longer resistance arm because taas man na. So it's long. So if we are going to flex the knee, you will have now short resistance arm. At the same time, you will encounter a little bit of decrease in the amount of resistance you're encountering. So therefore, the shorter the resistance arm, the lesser the load applied, or not necessary, the lesser the effort of the the muscle to raise the leg, no? Ano man siya, so inversely proportional na siya ang relationship between the resistance arm and the effort arm, or the amount of force needed to lift the leg, no? So the longer the resistance arm, the greater the force that is needed to lift the leg. Ano, directly proportional rather, not inversely. Sorry for that. Inversely, directly proportional. Because when when the resistance arm increases, your effort arm, or your effort force or force needed to lift your leg also increases. Kung mag-short resistance arm, less pod ang effort force nga i-apply sa muscle to lift the leg, no, in friction. So, force vectors and their considerations. Force vector diagram. So vector forces can be combined when more than one force is applied to a body or segment. The combination of these vectors will result into a new vector called resultant vector. So of course in in algebra, we have already the sum of all vectors, diba? In Cartesian coordinate system, wherein we are asked to add all vectors or vector quantity, no, the sum, not the product, the difference of all vectors, diba? Wherein you are going to add using head to tail, parallelogram, but we have those in our algebra as well as in our applied physics. By adding or subtracting more forces, their combined effect creates a single resultant force. So inana siya sa vector, di ba? So we have here now uh, the vector. So we have force vector A, example, from point, there is ito nga, point A, and force vector B. one vector goes to the opposite side or to the left, and the other goes to the right, which is the positive. Diba? Kung napa na siya, if there's already an x-axis here, a y-axis, all vectors that goes down on the y-axis is it is also a negative, and all vectors that goes up is positive, diba? So if we have a magnitude of 75 pounds going to the right and also a 75 pounds going to the left, unsa may ilang product? Zero, no? Di ba? So if we are going to um, sum it all, so zero na siya, di ba? So, ana. So composition of forces. So we have here, no? Uh, let's take for example, if we have A, no, we have a force directed up of A, then we have another force of B in the same direction. So if you're going to add the two, you just add it by using head to tail. So if you're asked for the resultant force, so force A plus 4V, that will give you force AB. So it means to say that you have to add the magnitude of the two since they are traveling in the same direction. So let's take for example, if we have this, no? We have force A, force B, force C, and they have different direction. All we have to do is to draw the forces in head to tail manner. So you have A, which is this one here, then B, so the same magnitude. When you say the same magnitude, the same lang, the length of this arrow should be the same. So then C. So you put it from head to tail. So this is the head of the other force, and this is the tail of B. Is you just put it there, no? Then C. So all you have to do is to connect them from head to tail. Then your resultant force is this one. It's the D. So you have to do now is to measure. So if you're using a scale, if you're going to draw it in a graph, and you use a scale that so scaling is very important in this one. So if you are using a scale, let's take for example, this is 2 centimeter length and force A, and 3 ang B, and C is equals to 4, no? So bali 4 boxes. So the same amount, no, sa scaling will be here. So if you're going to measure there using your scale, one box is to 2 centimeter, then if this is equivalent to 4 boxes or 5 boxes, you just multiply it by 1 centimeter, then you will have 5 centimeter, no? Ang imong resultant force. If it is in terms of Newton, 1 box is to 1 Newton, then this is equivalent to 6. Oh, 6 Newton. 5 Newton rather, if you have 5 boxes here in your uh, resultant force. Now let's take for example now. These are example of the force applied, no? Applied force ni siya, no? Applied physics. So you have here a weight added in the legs. Let's take for example, if you are trying to exercise, usually you put ankle weights, diba? Sa ankle. So you have here summation of forces acting along the knee joint. So if you notice now, I'm going to remove that one. So if you notice here, so what are the forces acting on the knee joint? First, you have the weight of the bone, which is towards the ground, and the load, this one. the load weight, or the load of the ankle weight, or the weight of the ankle weights, the ankle weights, no? So ana siya dira. So if you are asked to solve for the resultant force, then you can use your computation, di ba? The equation now will be minus 6 pounds, that is the weight of the leg and foot, and your uh, minus 3 pound, which is the weight of the boots. No, you consider pa the weight of the boots here, because the patient is wearing the boots, and the weight of the ankle weights, which is 10 pounds. Now, how do we come up with this negative sign? Because all of the weights is directed downward. So, in addition of numbers with negative sign, we just simply add the numbers or the magnitude, then follow the sign. So, resultant force is equals to 19 pounds. That is only the RF, the half of the magnitude. If we want to go to really know in Newton, so we must convert this into kilogram, diba? But if we will not convert it into kilogram, then we will multiply this by 32.2 feet per second. The unit there is not in Newton, but rather in slug, which is the English system, no? But if you are going to use the metric system, then we must convert the 19.5 pounds into kilograms, wherein one kilogram is equivalent to 2.21 pounds. So in order to convert this, we must divide this by 2.21 pounds. So we get the kilogram now, and we will multiply this by 9.8 meters per second in order for us to get the units in Newton. Unit of force in Newton. So we have here another problem. So here, head. If you are going to familiar with this is an example of sustained traction or continuous traction of the neck of the neck of the individual. No, so maybe na ano siya, the patient is suffering from uh, shall we say, stiffness of the neck muscle, and you need to relax the muscle. So one way of relaxing the muscle is to stretch it. No? Uh, Sustained traction. So we have here a weights in which the direction of the weight is 25 kilograms. Of, as we all know, it is directed downward on this system. But if we are going to consider this system, that direction, because we have here a pulley, again in anatomy, diba? The anatomic pulley changes the direction of the force, no? Without affecting its magnitude. So here we have a pulley. So if we are considering this system, the direction of the pull is towards upward, no? In upward direction. And the magnitude of that pull is about 25 pounds here, because they have the same magnitude, di ba? As I've said a while ago, without changing its magnitude. No? So, definition sa anatomic pulley. Okay? And it is going up. Then we have, what are the forces acting? Of course, the weight of the head, which is directed downward. And now, if you are asked for the resultant force, just simply you add your plus minus. Since you have your 25 pounds, which is going up, which is positive, so 25 pounds minus 10 pounds, which is the weight of the head, going downward, so you have an RF of 15. Again, this is not in Newton. No, so pwede na siya nimo i-convert. Okay, so inana ra siya, no? That's how. Then we have a lever system. So a simple machine what is a lever? That's the question. A lever is a simple machine that consists of a rigid bar that rotates around an axis or fulcrum. So here, we are talking here a translational force. No, translational. There's no rotational yet. No, but here, when we talk of the lever system, it's a rigid bar that rotates around an axis. In biomechanics, the principle of lever assists in visualizing the more complex system of forces that produce rotatory motion in the body. So basically, in our body, lever system exists because when we move, the joints rotate and the shaft moves also in rotational direction. Applying the concave convex rule, it might be the atrokinematics is opposite and the osteokinematics is towards or opposite direction. If we are going to use the concave convex rule, which is true in our joint surfaces. The perpendicular distance from the axis to the line of action of the resistance is the resistance arm, while the perpendicular distance from the moving forces to the axis is the force arm. So here we have now the term resistance arm and force arm. So look at the definition. The resistance arm is the distance from the axis to the line of action of the resistance. Okay. Because about it means to say wherever the load is located and from the axis of rotation to the load location is considered as resistance arm. While the distance from the effort arm or where is the muscle exert effort to the axis of rotation, we call that as your force arm. So here, let's take for example. So we have here now the first class lever system. First class lever system wherein the fulcrum is located at the middle and the resistance arm is located on the other side and the force or the effort arm is located on the other side. So if we are going to use now the definition of the perpendicular and the resistance the resistance arm and the force arm here. Let's take for example, this is the force. So distance from A to this one, this is your force arm, and from here to here is your resistance arm. So an example of first class lever system is this one. No? The Atlanto occipital joint. We call that as the yes and no joint. No? Well, that's an example of lever 1, wherein our head is moving back and forth in the atlanto-occipital joint. So here, your atlanto-occipital joint serves as your axis of rotation. At the same time, it is where also your fulcrum is located. So the weight of the head is your resistance arm, while the contraction of the semi-spine, no, the capitis muscles. No? So it could be a longissimus capitis, or it could be a semi-spinalis capitis. No, capitis means its head. No? So so this one, this is your the distance from here from the fulcrum towards this towards the insertion of that muscles. Okay, it is where the force exerted was the insertion. So that is your force arm. This one, this is your resistance arm. So now the note of this is that if it is moving along the clock direction, that is a positive. If it is moving counterclockwise, that is a negative. So here, if you are going to put that in mathematical form, so you have R minus F. No? if you want to solve for the torque. We call that as the torque. No? So the next one, so we have here the second class lever system. Okay. In the second class lever system, the fulcrum is located on the other side and the effort arm is in the middle, or the force arm, the resistance rather, or the load is in the middle, and the force is found on uh, the end. No, so we must remember that, no, that the resistance is in the middle. No, that's our key there. So the fulcrum is on the other end, and the effort or the force is applied on the other end of the fulcrum. So therefore, with this kind of lever system, you can carry a greatest amount of load with less amount of force. Okay, this one. So example of that is your wheelbarrow. Diba? In wheelbarrow, you can put 3 sacks of maybe cement here, and you can still lift, no, the wheelbarrow and move it in a distance. Diba? So great load with less effort. Okay. Now, so in here we have here the force arm. So the force arm, it starts from your fulcrum to where the force exert, while your resistance arm, again, it's a perpendicular distance from the fulcrum to the force where, or the resistance where it is located. So it is sample of the second class lever system in the body. So we have here, when you try to tiptoe, diba? When you tiptoe, that is an example of your second class lever system in the body. So you have here the resistance or the load, which is your body weight, and your effort arm. Your effort arm is here from the fulcrum to the force where the uh, from the fulcrum to the line of force of the Achilles tendon. This one. Okay. So this is the line of force of Achilles tendon. So perpendicular to that, that is your, this one, from here to here, that is your uh, force arm. So with this, only a small amount of exertion of your gastrocsoleus muscle, you can easily lift your body weight. Less effort, but with great load. So that is the second class. So usually the second class lever system is can be easily identified if you are doing closed chain kinematic movement. So in closed chain kinematic movement, usually you are using second class lever system. Then you have your third class lever system, which is very common in the body. So in this lever, the resistance arm is always away from the fulcrum, which means to say that the resistance is on the other end while the force is, or the resistance in the other end and the force is in the middle. So here, less load, oh no, less load, greater effort. Because the longer the lever arm, the greater the effort is needed in order to move that object. So this arrangement is designed to produce speed in moving the distal segment of the body with a small weight. So less movement happens on the proximal portion, but there's great movement on the distal end. So in this lever, the resistance arm is always longer to the force arm. So the mechanical advantage lies on the resistance force. So mechanically advantage resistance because there's a longer lever arm. So if you are going to multiply it with the force, the magnitude of that resistance becomes what? It increased drastically. So when it increased drastically, the farther that it goes away from the fulcrum, the more effort is needed to maintain that in perpendicular direction or in that position. Let's take for example, if you're holding a 1 kilo of rice when you're uh, with your uh, arms in side, your arms is inside or in your side. So of course you just need a very small amount of force, diba? You have clearly a kilo of rice, no? So when your arms is on your side, so it is very light. But try to extend or flex your arms in a straight line and move that forward. Put it in your front with your arms extended there in your front, and there's 1 kilo of rice hanging on it. Can you imagine the effort that is exerted by your shoulder muscles in order to maintain your arms in forward position? So because you suddenly change the length of your resistance arm, no, to what? To greater amount, no? Uh, Bigla mo nyo siyang pinahaba. So kailangan mo ngayon medyo mag-exert ka ng effort para maka-maintain siya in that position. Okay? So here this is very common because usually we move along the space or in an open space in open kinematic chain. So let's take for example, when you try to kick the ball, that is an open kinematic chain, and you are using third class lever system in extending your knee because you are extending it in open air. The resistance is on or far from the effort arm or from your force exerted by your muscles. Okay, so third class. So when you do that, you produces now what we call torque. Okay, torque is a force which is applied around an axis. Therefore, torque produces joint motion. So here, okay, this is where the torque happens. No? So it is a rotational force in the joint. So when force is applied around an axis, the product of force times the perpendicular distance from each line of action to the axis of motion, okay, or it is the potential motion if the object is currently stationary. So let's take for example here, where is the axis of motion? So here in the shoulder, where is the resistance? Here. But of course you have also the weight of the arm. And what muscles is maintaining this arm in this position? Of course, the shoulder muscles. Where we can find the shoulder muscles, especially the insertion here along the greater tuberosity and lesser tuberosity of the humerus. So the distance from the axis of motion to the insertion of the shoulder flexor muscle, that is your uh, force arm. While your resistance arm, you have two resistance arm. First, the distance from the axis of rotation to the line of action of your weight of the arm and line of action from the load. Okay, so that's it. No? So using now your mathematical equation, torque is equals to F times D, minus if it is clockwise or counterclockwise, so, or plus, okay, here. Then you have the load, which is load times distance from the axis to where it is located, minus from the weight of line of action of the weight of the arm times the resistance arm from the axis to the line of axis of the arm. That will be your torque. No? Okay. So here, this is an example. So I'm just going to stop on this portion. Okay. Then let's continue our discussion next meeting about this with more vivid illustration. Okay, thank you for listening. See you next meeting.